In a previous video, we looked at the concept of conditional probability. And conditional probability, it gave us a way of measuring how the occurrence of one event changed or affected the likelihood of another event occurring, right? And we came up with this nice formula. Let me remind you of the formula. So the probability of A given B, right, is equal to the probability of the intersection of those two events divided by the probability of B, provided the probability of B is positive, because we don't want 0 in the denominator, right? So this was our nice, relatively simple formula for conditional probability. But the thing is, the occurrence of one event, it doesn't always have to have an effect on the likelihood of some other event occurring, right? In other words, this is our first sort of informal definition of independence, and then I'll do an example to illustrate the idea and give a more formal definition with a nice formula that will actually take into consideration this formula, right? So there is a relationship between what we previously looked at as conditional probability and now this new concept of independence. We're just kind of building and looking at a special case. So let's define it informally. So if A and B are events such that the occurrence of B does not affect the likelihood of the occurrence of A, right? We say that A and B are independent, right? So we say A and B are independent, right? So the fact that B has occurred will not change the likelihood of A occurring. So let's take a look at how this might actually play out with an actual experiment, and I'll define two events, and we will argue that these events are in fact independent, right? So let's take a look at this example. And it's a really simple example. So here's our experiment. We are going to toss a coin, let's say a fair coin. That means it's not weighted, where one face is more likely to show up than the other. So toss a fair coin and roll a fair die, right? So roll a fair die. Okay, so that's our experiment. Let's define our event. So define A to be the event where we observe a head. Right, so observe a head. And then B be the event that we observe, let's say a 5. All right. Well, I mean, these two, we can compute their probabilities really easily because, these are very small sample spaces, and we know, for instance, here we're just looking for when you toss a coin, there are two possibilities. And if we assume that they're equally likely to occur, then that's the 50-50 case, and we can say that the probability of A is 1/2. And similarly, again, with a fair die, there are 6 possibilities, and we're just looking for this one, so we can say that the probability of B, again, is 1/6. But now let me describe the experiment in a different way. Like the way I have it here, where I say toss a coin and roll a fair die, it almost implies in some sense that we're doing both of these simultaneously, right? So, I'm not super coordinated, but I think I could probably pull off tossing a coin and rolling a die at the same time, and then we can see what shows up. So we will either A will occur or not, or B will occur or not, but we'll be able to make both observations pretty much simultaneously. And you might say, okay, well, that's fine. I can think about all the possibilities. But the thing is, I can describe the experiment in a slightly different way that will lead to the exact same sample space, right? And it will give us a clearer idea of this concept of independence. So instead of thinking of it as a simultaneous toss and roll, what if we did it in sequence? So what if we first tossed the coin so we knew what the outcome of the toss was, and then we ask ourselves, how is that going to affect the likelihood of what happens on the roll of the die? So in other words, so if we toss, then roll, right? So now think about it that way, and then let's ask ourselves this question. What is the probability that we observe a 5 given that we've observed a head, right? So in other words, we perform these in sequence, so it's like we know the result of this, and then we're halfway to completing our full task, and then we ask ourselves, well, now I'm going to roll the die. What's the probability that I'm going to observe a 5? Well, it's still going to be 1/6, right? So regardless of what happened when we tossed the coin, heads or tails, it doesn't change the likelihood of the occurrence of a 5. Because as far as rolling the die is concerned, right, the sample space still consists of 6 elements, and still only one of those 6 is what is defined in this event. So again, just kind of thinking it through that way, we realize that it doesn't really matter what happens on the toss. The probability of B occurring is still 1/6, which is exactly the probability of the B itself. So B, right? The likelihood of B is unaffected by the occurrence of A, right? And it's really an interesting thing, this idea, like when you're doing multiple actions or multiple processes, many times you have to ask yourself, does it matter if I do them simultaneously or do I do them sequentially? And in this case, because the events are independent, it doesn't matter, right? It doesn't change the likelihood here. All right. So with that in mind, let's write down our little equation that will give us a working definition for independence, right? And in fact, what we're going to do is take this cue and just say, yeah, if the probability of one event given some other event is the same as the probability of that event, if there's no change, right, with the conditioning, then we're going to say that they are independent, right? So here is our definition. And it really just symbolizes what we've been saying in multiple ways. So given A and B, right, that are events in some sample space, A is independent of B if and only if, so if, and definitions are usually understood to be if and only if, so, but sometimes we say it for emphasis. So A is independent of B if and only if this is true. the probability of A given B is always equal to the probability of A. And if you remember, I described this as a prior probability. So before any additional information is garnered, and then this was like a posterior probability after the fact. So two events are independent if the prior of one is equal to the posterior of it conditioned on some other event, if those are equal, right? And that's our working definition of independence. Now, going back to this example with the toss and the roll, what if we changed the order? So again, remember we did it in sequence here. We toss and then we roll. Right? That could be a song or a dance or something. But anyway, so we toss and then we roll and we came up with this. But what if we flip it around? What if we roll the die and then we knew the result on the die and then we questioned ourselves like what is the likelihood of observing a head now that we've known that we got a 5 or didn't get a 5 for that matter, right? Well, it would still be the same, right? So what would happen is that in that sense, so what I'll just say similarly, so if over here we roll, then toss, look at what happens, right? So I know, so given I know what happens on the roll, what's the probability of us getting ahead on the toss of the coin? Well, it's still 1/2, and that's still the probability of A. So what this tells me is that if A is independent of B, then B is independent of A. So if this is true, this is true. If this is true, this is true. So that's a nice little observation to note, right? So essentially what we can do is we can be a little bit more precise in saying this. So I'll just make this say this, that this is a note. If A is independent of B, then B is independent of A, right? Not only that, we can say even more. What if we don't get ahead? So what if we, what if we said, okay, well, what is the probability of B given A complement, right? Again, so whether or not we observe a head on our toss, it doesn't affect the likelihood of getting that 5, right, on the roll. So the probability of getting a 5 on a roll is still 1/6, which is still the probability of B. And then we could do the same thing over here and say, well, what if we don't get a 5? That's still not going to affect the probability of getting ahead. So I can say this too. The probability of A given not B, that's still 1/2. That's still the probability of A. So we can make another observation. Right, and this is probably the most general we could say. If A is independent of B, then all these other combinations of events are also independent. In other words, this. If A is independent of B, then I'll say the following pairs of events are also independent. So then the following pairs are also independent. So obviously A and B are independent, but what this shows is that A complement and B are also independent, right? So A complement and B, and then A and B complement. That's what this shows over here. This shows this equation over here, this little example. Again, I should say these are illustrating these ideas. These are not considered formal proofs. But the fact that conditional on B not occurring, the probability of A stays the same as it was before we got that added information, then it means that these two are independent. And then also it turns out that A complement and B complement are also independent, right? So the probability of not observing a 5 first, right, does not change the probability of not observing a head, right? So once you know a pair of events are independent, then it means all these other pairs have to be independent. So you can take the concept of independence and it scales pretty quickly, right? So here's our definition, right? Now there's a nice formula that comes as a result of this, and this is something I will prove. I didn't want to prove too many things in one video. I wanted to again kind of hit home that concept. But yes, here's a particular result, and in fact, what I'll do is I will um, I will give you the proof first and then state the theorem after. So we're just kind of playing around with definitions now. We have two definitions that we can work with, right? So we know that the probability of A given B is equal to the probability. So this is for all events now, right? This is what we looked at previously, the conditional probability. This is how it's defined, right? This is by definition, right? So we know that. The other thing we know is what we just defined above. We just defined, we came up with the definition for this if we know that they're independent. So now, additionally, if A and B are independent, so this is an added condition now that we know, right? So if A and B are independent, then let's write that definition down. We know that the probability of A given B is equal to the probability of A, right? That's what we just defined up above, right? If two events are independent, the fact that one event has occurred does not change the likelihood of the other. So the prior is equal to the posterior, right? But look at this. Just look at the way I have this written. I have the same expression here as I do here. So now if we know that the events are independent, because these two expressions are the same, right? Then these two expressions have to be the same as well. That's the transitive property. If A is equal to B and B is equal to C, then A is equal to C. So connecting the dots, connect it like this. If the probability of A is equal to the probability of A given B, and that occurs when the events are independent, and we know that the probability of A given B by definition is this ratio, so therefore, again, under independence, we have this really nice relationship. I can set these two things equal to each other. So therefore, this fraction, this ratio that I have over here, the probability of A and B over the probability of B, that's equal to the probability of A. Right? Again, this is only for independence. This is a special result, but now I can write this in a really nice way and say that the probability of A intersect B is equal to the probability of A times the probability of B, right? And this is probably one of the most powerful results that you can get out of independence. It's saying if you know, and again, I'll restate it in the theorem because of how important it is, but if we know that the events are independent, then the probability that they both occur is equal to the product of their individual probabilities, right? So the probability that of A and B is equal to the probability of A times the probability of B, assuming they are independent. And that's what the theorem says, and that's essentially the proof. The proof just uses the two definitions and that transitive property of numbers. So here is the theorem, and this is only for, it's sometimes referred to as the multiplication rule for probabilities, because that's what happened on the right hand side. So I'll state it like this. So this is the multiplication rule, but now not for counting, but instead for independent events. Right? So for independent events. Long title for a theorem, but it's an important one, so it deserves a long title. So again, let me just state it. So I'll state it as simply as I can. If A and B are independent events, then this is the conclusion. The probability of A and B is equal to the probability of A times the probability of B, right? And that's our theorem. So what I want to do is just end the video with a quick example, just showing how you would use this. But it's not an example where we're going to answer. It's not an example where we're going to answer lots of different questions. What I want to do is just to show you how, if I know three things, if I know the probability of A, the probability of B, and if I know that they're independent, I can use that information and complete our Venn diagram, right? And then remember, once we have the Venn diagram completed, we can answer any type of question related to those two events, right? So let's end with this example. So suppose, and when these questions, and statements are made, look out for that additional assumption of independence, because if you know the events are independent, it means you can answer questions a lot more efficiently, a lot more effectively. So suppose A and B are independent events with the probability of A. So let's say the probability of A is 1/5 and the probability of B is 1/3, right? So that's given to us. But now we know that they're independent, and I'll just write down the instructions. Set up and complete a Venn diagram that illustrates this, right? So construct the corresponding Venn diagram or something to that effect. So construct the corresponding Venn diagram, right? And the reason why I'm not going to go beyond this is simply once we have the Venn diagram completed and we've seen it, um, play out in previous examples and previous videos is that once you have the Venn diagram, as long as you know how to read the information in that Venn diagram, then you can answer pretty much any question, right? So let me start with the Venn diagram, and I think what I will do, yeah, so let's move things over there. I'm going to put the Venn diagram here on the left. And what we have are these two circles. And we have the A and B. So to fill it out, as usual, we like to start in the region where the events overlap. So that overlapping region right there. And remember, that region right there represents the intersection of the two events. So let's see if we can figure out what probability needs to go in here. Once we can figure out that probability, we can work our way outwards until we have the entire Venn diagram completed. So you might say, well, how am I going to do that? Well, when all I have is the probability of all of A, which is 1/5, and the probability of all of B, which is 1/3. Well, that's not all that we have. We have the fact that they're independent. And I have this formula previously that tells us what we can do to find the probability of the intersection. So to start out in the middle, since the events are independent, right, we can say that the probability of the intersection is simply the product of the probability of A and the probability of B. So yeah, and we have this, right? So once we have these two separate ones and the knowledge that the events are independent, we automatically get this by doing a simple product. So this is 1/5 times 1/3, so then that's 1/15. So now I know in here it's 1/15. And then once I have that, I use our previous procedures to complete the rest of the Venn diagram. So to figure out the part that's only A, and here let me write it out in words so you can see it. So the probability of only A, that would be the probability of all of A minus the probability of the intersection of A and B. So I'll write it like this. You take the entire probability of A and then minus the probability of the intersection of A and B. So take the 1/5 and subtract the 1/15, what we just found. And then that will give us the only A part. Okay? So 1/5 is the same as 3/15 minus 1/15, so that's 2/15. So that goes right here, right? So given the fact that we have two more regions to complete, our progress bar is 50% there. So hopefully that makes you happy. So then let's do the same thing to figure out only B. So the probability of only B, and we could go ahead and express this in terms of complements and all that stuff. I just wanted to write it out in words. You know, it's good to do things in different ways, right? So you don't get stuck in one, I don't want to say rut, but just in one mode of doing things. When you do that, sometimes you just put blinders on and you lose sight of important connections. So only B is the probability of B minus the probability, again, of the intersection. So that's the probability of 1/3 minus 1/15. So 1/3 is 5/15 minus 1/15, so that's 4/15. So that goes here. And then to complete the everything that's so like not A or B. So the probability of let's say it this way: neither A nor B. So use our first axiom, saying that everything in the rectangle has to add up to 1, we know what adds up inside the circle, so the difference between 1 and the sum of these probabilities will give us the probability of neither A nor B. So let me write that down. So it's 1 minus the sum of what we've just figured out. The 2/15ths, the 1/15th, and then the 4/15ths. And that's, so what's that? So that's 7/15ths. So 15 minus 7, that's 8. So 8 over 15 goes outside. Right? And once we've completed our Venn diagram, now I can ask you to find any probability of any combination with all our set operations of these two events, right? So it's like we gain this property, and even though we weren't given the probability of the intersection to start with, we can compute it based on the result that we just proved. All right. So independence, very, very important. In fact, statisticians love independence because it plays a big role in a lot of their theorems, and we'll see some of those later on in this course. But for now, we just get to enjoy and utilize this property that will help us answer more probability questions, right? And we'll do so in the next video.